Hello student, welcome to my channel The Learn Physics. I have already uploaded the Ncert chapter 1, Ncert chapter 2, Ncert chapter 3, Ncert chapter 4. Today I will be discussing the chapter 5 of class 12 Ncert. Now my discussions are magnetism and matter. The subtopics are, first of all, introduction, that is the properties of magnet. Number 2, bar magnet, magnetism and Gauss law, earth magnetism, magnetization and magnetic intensity, magnetic properties of material and permanent magnet and electromagnet, and the Ncert numericals of all the topics related with it. Now, first of all, some commonly known facts about magnetism. Number 1, Earth behaves as a magnet with magnetic field directed from approximately geographic south to geographic north. When a bar magnet is freely suspended, it orients along the north-south direction. The tip which points towards the north is called North Pole, and the tip which points towards the south is called South Pole. Number 3, two like poles repel each other. That is, when a two North Pole or South Pole are brought close to each other, they repel each other, and unlike pole attract each other. That is, North Pole, South Pole attract each other. We cannot isolate North Pole or South Pole. If we cut a bar magnet at its midpoint, then we get two magnets of weaker strength. So magnetic monopole is not existed. It is possible to produce a magnet with iron or alloy of iron. Okay? Now next, bar magnet. Bar-shaped magnet is called bar magnet. Its one end is North Pole and other end is South Pole. The North Pole and South Pole are not at the extreme end. It is slightly inner of the ends. The distance between South Pole and North Pole is called magnetic length. Generally, we take magnetic length as 2L. So look at this, the magnetic length is slightly smaller than geometric length. Now magnetic moment. The magnetic moment of bar magnet is directed from S to N, and it is represented by small n. Its unit is ampere meter square or joule per Tesla. Its dimension AL square. Okay? Now magnetic field on the axis of a bar magnet. The magnetic field on the axis of a bar magnet, B vector equal to mu naught by 4 pi 2 m vector divided by r cube, where r is the distance of the point from the center of the magnet, and magnetic length twice L is very small, then smaller. Now magnetic field on the perpendicular bisector position is directed along this direction. If this is the magnetic field B axis and this is the B perpendicular bisector position, so look at this B perpendicular position, look at this direction is this direction, but magnetic moment M this direction, so this is becomes minus mu naught by 4 pi, this is the M divided by r cube, where twice L or L is less than smaller. Therefore, the magnetic field at the perpendicular bisector position is half of magnetic field at its axis. Understood? Now, magnetic field lines. Magnetic field lines are visual and intuitive realization of magnetic field. Now look at this, magnetic field are closed line. So look at this, from this to this, it's south pole, and then again inside the magnet from south pole to north pole. So look at this, magnetic lines of force originate from north pole, and now it's enter into the south pole, and inside the magnet it moves from south pole to north pole. So it is a closed line. Now the tangent at any point, look at this, at this point represents the direction of magnetic field. Now this point, look at this, represents the direction of magnetic field. This point represents the direction of magnetic field. Okay? Now properties of lines of force. Number 1, the magnetic field force are continuous and closed. Number 2, the tangent at any point of these field lines gives the direction of magnetic field. Number 3, if the lines of forces are closer, then field is stronger. Next, two field lines do not intersect each other. If they intersect, at the point of intersection, two tangents can be drawn, which represents the two directions of a magnetic field in a given point. This is impossible. Okay? Now next. Now look at this Ncert numerical 5.12. Look at this. This is a small bar magnet of magnetic moment small m and magnetic moment directed along this direction. The magnetic moment is given 0.48 Joule per Tesla. We have to calculate the magnetic field and its direction on the axis and perpendicular bisector position at a distance 0.1 meter from its center. Look at this, on the axis, the magnetic field is directed as the direction of m vector, and on the perpendicular bisector position, the magnetic field BP is directed opposite to the m vector. Okay? Now, first of all, BA. Look at this, BA equal to mu naught by 4 pi divided by 2m divided by r cube. Look at this, this is the 10 to the power minus 7, this is the 2 into 0.48, and this is the 0.1 whole cube. So look at this, this is the 0.96 into 10 to the power minus 4 Tesla. Okay, that is 96 micro Tesla, and it is directed along the direction of m vector. Now on the perpendicular bisector position, mu naught by 4 pi, this is the m by r cube. Look at this, this is the 2m by r cube. So magnetic field at this point is half of this. So here this equals to 48 micro Tesla, and its direction is opposite to the direction of m vector. Okay? Now next. Now the similarity between bar magnet and solenoid. Look at this. This is a bar magnet. Okay? And look at this. This is a solenoid. Now the magnetic field due to solenoid is directed along its axis. In the same way, the magnetic field due to a bar magnet is directed along its axis. Now its magnetic moment m equals to NAI, where n is the total number of turn, A is the area of cross section of each turn, and I be the current passed through it. and one end of solenoid represents S pole and other represents N pole of magnetic moment NAI. In the same way as that of bar magnet, which also represents one end south pole and other end north pole having magnetic moment directed from south pole to north pole. Okay, the magnetic field due to solenoid at its axis on the long distance B equal to mu naught by 4 pi, this is the 2m by r cube. In the same way, the bar magnet also produces magnetic field mu naught by 4 pi, this is the 2m by r cube. Okay, understood? Next, now Ncert numerical 5.5. Look at this, a solenoid has total number of turn 800 and area of cross section of each turn is 2.5 into 10 to the power minus 4 meter square and current passed through it is 3 ampere. Now, what is the magnetic moment associated with the solenoid? We know the magnetic moment associated with the solenoid is NAI. Here n equal to 800, this is the 2.5 into 10 to the power minus 4, okay, into 3, this is the ampere meter square or joule per Tesla. Now this and this is the 2000, okay, and 10 to the power minus 4 into 3, so this is the 0.6 ampere meter square. Therefore, this is the magnetic moment associated with a solenoid. Okay, now next. Now force and torque on a dipole in a uniform and non-uniform magnetic field. Suppose this is a uniform magnetic field B, here a magnet N pole and here a magnet is placed here. Now look at this, if B be the strength of magnetic field, the N pole experiences forces, this is the Qm into B, and S pole experiences the forces, this is the minus Qm into B, where Qm and minus Qm are the pole strength of north pole and south pole. So net force on this dipole is 0. Now torque experienced by the dipole in this magnetic field, tau vector is equal to m vector cross b vector. Now the magnitude of torque tau equal to m b sin theta, where theta is the angle between this is the m vector and this is the b vector. So theta is the angle between m vector and b vector. Okay, now potential energy of the dipole in this magnetic field. Now the torque experienced by the magnet is mb sin theta. Now work done to turn it from theta to theta plus d theta is, this is the tau into d theta. So this is the mb sin theta d theta. Therefore potential energy, this is the integration of 90 degree to theta, this is the mb sin theta. So now this expression becomes minus mb, this is the cos theta, and this is the theta to 90 degree. So this is the minus mb cos theta. So this is the minus m vector cross b vector is the potential energy. Now work done to turn the dipole from theta 1 to theta 2. Now work done to turn the dipole from theta 1 to theta 2 is the difference of potential energy between final point and initial point. Now look at this, the potential energy at the final point, this is the mb sin, this is the mb cos theta 2 minus mb cos theta 1. Okay, so look at this is the mb cos theta 1 minus cos theta 2 is the work done to turn a dipole from theta 1 to theta 2. Okay, now what is the maximum work done? Look at this. If a magnet if a magnet turn from 0 degree to 180 degree, that is stable position to completely unstable position, then work done delta W become, look at this, this is the MB into cos 0 minus cos 180 degree. So this is the twice M into B. Okay, understood? Now next. Now look at this, a magnet of magnetic moment small m is suspended by means of a string. It is placed in an uniform magnetic field B vector. The magnetic dipole is turned through a small angle theta, then torque experienced by the magnet is mb sin theta. As theta is very small, so look at this, this is become mb theta. Now due to magnetic field, the magnet try to orient itself along the direction of magnetic field. So a restoring torque is produced. Now this restoring torque, this is the I d square theta by dt square equal to minus mb theta. Okay, now here d square theta divided by dt square equal to minus mb by I into theta. So this is the minus omega square theta. Look at this, the angular acceleration is directly proportional to the angle of turning. So it executes SHM in the magnetic field. If capital T be the period of oscillation, then look at this, T equal to 2 pi by omega. Look at this, omega square equal to this. So omega equal to root under of this. So this is the 2 pi root under of mb by I. Therefore T equal to, this is the 2 pi root over I by mb. Okay, understood? Now next. Now numerical 5.6 of Ncert. Magnetic moment of a solenoid is 0.6 joule per Tesla. The horizontal magnetic field is 0.25 Tesla. If the solenoid makes an angle 30 degree with the direction of magnetic field, what is the torque experienced by the solenoid? Look at this, this is the magnetic field. This is the horizontal magnetic field. Okay, now look at this, the solenoid, this is the solenoid, this solenoid, this is the solenoid. This solenoid makes an angle 30 degree with the direction of field. Okay, so look at this, tau equal to mb sin theta. Here m equals to 0.6, t equal to 0.25. Okay, and this is the sine 30 degree. So here look at this into this. So this is the 0.15 into half. So this is the 0.075 Newton meter is the torque experienced by the solenoid. Understood? Next. Now Ncert 5.7. A bar magnet of moment 1.5 joule per Tesla is aligned in a magnetic field of magnitude of 0.22 Tesla. We have to calculate the work done to turn from equilibrium position to its angle 90 degree, equilibrium position to an angle 180 degree, and we have to calculate torque at this position and at this position. We know the amount of work done to turn a magnet from angle theta 1 to theta 2 is cos theta 1 minus cos theta 2. Now look at this, theta 1 0 degree, theta 2 90 degree. So work done equal to, look at this, 1.5 into 0.22 into, look at this, this is the cos 0 degree minus cos 90 degree. So look at this, here 0.33 into, this is the 1 minus 0. So 0.33 joule is the work done in the first case. Now work done in the second case. Now delta W3 is equal to, this is the MB, this is the cos theta 1 minus cos theta 3. Look at this, cos theta 3 equal to 180 degree. So look at this is the 1.5 into 0.22 into cos 0 minus cos 180 degree. Look at this, cos 180 degree equal to minus 1. So this is the 1.5, 0.22 into 1 plus 1. So look at this is the 0.66 joule. Okay. Now torque acting on this position and this position. Now the torque tau 2 equal to mb sin theta 2, because we have to calculate the torque at this position. So here m equals to 1.5, b 0.22, and this is the sine 90 degree. This is the 0.33 Newton meter is the torque acting on the dipole. Now at this position, look at this, we know sine 180 degree equal to 0. So torque at this position, this is the mb sine 180 degree. So this is the 0. Okay, understood? Now next, when a magnet of magnetic moment small m placed in a magnetic field 0.25 Tesla at an angle 30 degree with the direction of the field, it experiences a torque 4.5 into 10 to the power minus 2. We have to calculate m, the magnetic moment. Now we know tau equal to m b sin theta. Now look at this, m equal to tau by b sin theta. Here tau equal to 4.5 into 10 to the power minus 2, b equal to 0.25, and this is the sine 30 degree. Okay, so look at this is the 4 and sine 30 half, so this is the 2 into 4.5 into 10 to the power minus 2 joule per Tesla. Okay, so look at this, here this is the 8. So this is the 36 into 10 to the power minus 2 joule per Tesla. Okay. Now next. Now Ncert 5.4. A bar magnet of magnetic moment 0.32 joule per Tesla is placed in a magnetic field 0.15 Tesla. The magnet is free to rotate in the field. Now find the potential energy when it is placed in equilibrium position, that is in stable equilibrium, and number 2 in unstable equilibrium. We have to calculate the potential energy in above two cases. Now potential energy U equal to minus mb cos theta. So in the stable equilibrium, this is the minus mb into cos 0 degree. So this is the minus mb, m equal to 0.32, and this is the 0.15. So this is the 0.048 joule. Again, when it is placed in unstable position, now this is u dash equals to mb cos, this is the 180 degree with negative sign. So look at this is the mb, so 0.048 negative sign, look at negative sign, into this is the minus 1. So this is the 0.048 joule. So in stable equilibrium, potential energy is negative, and in unstable equilibrium, potential energy is positive. Understood? Now next. Now Ncert 5.8. Look at this, a solenoid of area of cross section this, carrying a current I equal to 4 ampere and total number of turn is 2000 turn. We have to calculate the magnetic moment NAI. Now if this solenoid is placed in a magnetic field of strength this at an angle 30 degree, we have to calculate force and torque mb sin theta. So first of all, the magnetic moment M. Look at this, M equal to NAI. Look at this, N is the 2000, I equal to 4 and A equal to 1.6 into 10 to the power minus 4. Okay, this is the 4.8. So this is the 9.6 into 10 to the power minus 1. So this is the 0.96 ampere meter square is the magnetic moment of the solenoid. Now what is the force? As the solenoid is placed in uniform magnetic field, so net force on it is 0. So this is F equal to 0. Now what is the torque? Now torque tau equal to mb sin theta. Now tau equal to mb sin theta. Here m equal to 0.96 and this is the 7.5 into 10 to the power minus 2 and this is the sin 30 degree. Okay. Now sin 30 equal to half. So half into 0.96. So this is the 0.48 into 7.5 into 10 to the power minus 2. So this is the 0.36 into 10 to the power minus 1 Newton meter is the torque experienced by the solenoid. Okay. Now next. Now look at this, a circular coil of area pi into 0.1 whole square meter square carrying a current 0.7 ampere and it has 16 turns. It is placed in a uniform magnetic field 5 into 10 to the power minus 2 Tesla. The circular coil oscillates about its equilibrium position and frequency of oscillation is 2 seconds, so period is half second. We have to calculate moment of inertia. Now the period of oscillation 2 pi root over I by m into b. Now look at this, this is the t square equal to 4 pi square, this is the I by mb. So look at this, I equal to mb t square divided by 4 pi square. Now what is m? M equal to NAI. So look at this, this is the NAI, b, this is the t square divided by 4 pi square. Okay. Now what is the n? N is 16. A pi into 0.1 whole square, I equal to 0.75 and magnetic field, this is the 5 into 10 to the power minus 2 and now look at this, this is the t square. T square means 1 by 4 and final divided by this is the 4 pi square. Okay. Look at this, pi cancel out. Okay. Now 4, this is the 4, this and this cancel out. Now look at this, I equal to here 0.01. Okay. Now this is the 0.75 into 5. So look at this, this is the 5 into 0.75 into 10 to the power minus 2 divided by pi. Okay. This is the 1.2 into 10 to the power minus 4 kg meter square is the moment of inertia of the circular coil. Okay. And now analogy between electrostatic and magnetism. Now first of all, constant. Look at this, here constant is 1 by epsilon naught, but here constant is mu naught. Okay. Now dipole moment. Now dipole moment is here P and this is the M. Okay. The dipole moment is directed from negative charge to positive charge. Here dipole moment directed from south pole to north pole. Understood? Now equatorial field is equal to 1 by 4 pi epsilon naught P divided by R cube and directed opposite to the direction of dipole moment. And here same way, this is the mu naught by 4 pi and this is the minus m divided by R cube. Now axial field, this is equal to 1 by 4 pi epsilon naught this field directed along the direction of dipole moment and this field twice of this. In the same way, this field is also twice this and is directed along the direction of m vector. This is the m vector, this is the m vector. Now, the torque experienced by a dipole is p vector cross e vector. Okay, now here m vector cross b vector, the torque experienced by a magnetic dipole. Now, potential energy, this is the minus p vector dot e vector. Here potential energy, this is the minus m vector dot b vector. Okay. Now these equations can be replaced by this. If we replace 1 by epsilon naught by mu naught and P is replaced by M. Okay. Now Gauss law of magnetism. The magnetic flux in a closed surface is the surface integral of B vector dot ds vector. Now, in a closed surface, the number of entering field lines is equal to number of leaving field lines. So, net field lines becomes 0. Now, the surface integral of magnetic field, this equal to 0. Okay. Now, terrestrial magnetism. From following observation, it proves that Earth is a huge magnet. Number 1, a freely suspended magnet always orients itself along the north-south direction. Number 2, a magnet can be demagnetized if it is placed on the Earth's surface. Number 3, the iron bar orient along the north-south direction get a feeble magnetism. And number 4, the existence of Earth magnetic field is obtained from the long distance of Earth's surface. From this observation, it can prove that Earth is a huge magnet. Now, what is the cause of Earth magnetic field? Initially, it is regarded that a long iron bar placed along north-south direction, but is not so current. Second point, it was also considered that due to rotation of the Earth, the outer core of the Earth revolves. Due to revolution of this, a convective current is produced. Due to convective current, magnetic field of Earth is produced. This is known as dynamo effect. But this is not so correct. But this has not enough proof. Now, the last point, the tremendous amount of charge present at the ionosphere of the Earth. As Earth rotates, that is, with respect to the Earth, the charge also rotates. Due to this charge, the magnetic field may produced. Now, north pole of a bar magnet is called north pole because it seeking towards the north pole of the Earth. And south pole is also called because it is south seeking pole. Okay, actually the nature of north pole of a bar magnet and north pole of a earth magnetism is completely opposite. Now look at this, the north pole and south pole do not coincide with the geographic north pole and geographic south pole. It is slightly inclined. Now angle between geographic axis and magnetic axis is 11.3 degree. Now this is the north pole and this is the south pole. Here field lines enter at the north pole and emerge from the south pole. So nature of the north-south is completely opposite to the nature of north-south of bar magnet. Okay. Now the elements of earth magnetism. Number 1, the angle of declination. Okay. Number 2, angle of dip. And number 3, the horizontal component of earth magnetic field. Okay. Earth magnetic field. Okay. Now we discuss one by one of this. Okay, now geographic meridian. The geographic meridian of a place is a vertical plane passing through the point of the place, geographic North Pole and geographic South Pole. Okay. Now magnetic meridian. The magnetic meridian of a place is a point passing through magnetic South Pole, magnetic North Pole and the place. Okay. Magnetic South Pole, magnetic North Pole and the place. Now the angle of declination is the angle between the magnetic meridian and the geographic meridian. If the magnetic North Pole is west of geographic North Pole, then its declination is called theta degree west. The angle of declination of London is 10 degree west. It means the magnetic North Pole is 10 degree west of geographic North Pole. Okay. Now angle of dip or angle of inclination. The angle made by freely suspended magnet with the horizontal direction is known as angle of declination, or angle made by the total magnetic field with the horizontal direction is known as angle of dip or angle of inclination. It is denoted by I. Okay. The angle of dip or inclination of Kolkata is 31 degree north. It means a freely suspended magnet makes an angle 31 degree with the horizontal direction and its north pole below the horizontal line. Okay, I show the angle of declination, the angle of inclination, horizontal component of earth magnetic field. Now this is the cuboid. Look at this. This line suppose represents the geographic north pole and this line represents the magnetic north pole. So look at this, the angle between geographic north and geographic south with respect to this point is called angle of declination D. So this is the D. Okay. Suppose a freely suspended magnet placed here. This is the N pole and this is the south pole. So direction of earth magnetic field directed from south pole to north pole, and this is the E vector. Angle made by total earth magnetic field with this horizontal line is known as angle of dip or angle of inclination. Okay, so the horizontal component of this along this direction, this is the HE equal to BE into angle of cosine of angle of inclination. So this is the cosine. Understood? And its vertical component, look at this, this is the vertical. Now its vertical component ZE equal to B sine of angle of inclination. Okay, the horizontal component of magnetic field along the geographic north is equal to HE dash is equal to HE cos capital D, where D is the angle of declination. Okay, here HE equal to, this is the BE into cos I, and JD vertical component, this is the BE into sin I. Okay, if this divide this, so look at this, ZE divided by HE, this is equal to tan I. So tangent of angle of inclination is the ratio between vertical component and horizontal component of magnetic field with respect to the magnetic meridian. Now with respect to geographic meridian, look at this, suppose with respect to geographic meridian, the angle of dip or inclination be I dash. So look at this, tan I dash, this is equal to the vertical component in the geographic meridian divided by horizontal component in geographic meridian. Now horizontal component geographic meridian is HE dash. Now look at this. This is the JD divided by HE cos D. Now look at this. This is the tan I. So here tan I into sec D is the apparent dip with respect to geographic meridian. Okay, understood? Now next, look at this. This is the magnetic north pole. This is the magnetic south pole of Earth. If a bar magnet is placed north pole pointing towards the north, look at this. This is a bar magnet whose north pole pointing towards north. Now look at this. The magnetic lines of force from south pole to north pole. Look at this. Along this direction, and from here, and now here, this is the direction of magnetic lines of force. This is the direction of magnetic lines of force. So on the perpendicular bisector point, now on the perpendicular bisector point of this magnet, a point is obtained where the magnetic field due to bar magnet is equal to the magnetic field due to earth magnetism. So the resultant magnetic field at this point becomes 0, and similarly this point also 0. Now if horizontal component of earth magnetic field be HE and magnetic field due to bar magnet is mu naught by 4 pi, this is the m by r cube, where r is the distance of this point from the center of the magnet, then this equal to this. Okay, so at the neutral point where magnetic field due to bar magnet and magnetic field due to horizontal component of terrestrial magnetism are equal and opposite. So here HE equal to, this is the mu naught by 4 pi into m by r cube. Understood? Look at this. If magnetic north pole pointing towards south or south pole pointing towards the north, now look at this. Here lines of force starts from this way. Okay, now due to south pole the lines of force moves along this direction, so we get a point on the axis. So we get a point on the axis where magnetic field due to bar magnet is equal and opposite to the horizontal component of earth magnetic field. Okay, so neutral point is obtained this point. If distance of this point from the center of the magnet be r, then mu naught by 4 pi, this is the 2m by r cube equal to horizontal component of earth magnetic field. Okay, now next. Now Ncert 5.10. Look at this. Here angle of inclination or dip is given. Horizontal component of earth magnetic field also given. We have to calculate the magnitude of earth magnetic field. We know BE equal to, this is the HE divided by cos I. Look at this. This is the 0.35 and this is the cos 22 degree. Okay, this is the 0.38 Gauss. Understood? Now next. Now 5.11. In Africa, the angle of declination is 12 degree. Now look at this. This is the magnetic north. Okay, and this is the geographic north. Okay, now angle of declination 12 degree. So this is the 12 degree. Okay, now a freely suspended magnet makes an angle 60 degree with the magnetic meridian. Now the horizontal component is given. We have to calculate the earth magnetic field. Now look at this, as angle of inclination is I. So look at this, HE equal to, this is the BE cos I. So look at this, BE equal to, this is the B equal to, this is the HE by cos I, h equal to 0.16, and this is the cos 60. Cos 60 means half, so this is the 0, so this is the 0.32 Gauss. Okay, understood? Next, now Ncert 5.13, the magnitude of earth magnetic field 0.36 Gauss. The angle of dip is 0. So horizontal component of earth magnetic field is also 0.36 G, because H equal to B cos 0 degree. Cos 0 1, so this. Okay? As the neutral point is obtained on the axis, so the north pole of the bar magnet is pointing towards south and south pole pointing towards north. As neutral point is obtained on the axis, so horizontal component of earth magnetic field is equal to magnetic field at this point due to this magnet, and this is mu naught by 4 pi, this is the 2m by r cube. Now this is the 0.36, so this is the mu naught by 4 pi, and this is the 2m by r cube. Okay, now we have to calculate magnetic field at this point. Now magnetic field at this point due to bar magnet is directed along this direction, and magnetic field due to earth magnetism is also directed along this direction. So this is the HE and this is the B perpendicular bisector position. So total magnetic field B equal to HE plus BP. Now HE equal to, look at this is the 0.36 Gauss, and we know the magnetic field at the perpendicular bisector position due to the magnet is half of magnetic field on the axis. Now magnetic field on the axis is this, so magnetic field at this point is half of this, so this is the 0.18, so this is the 0.54 Gauss. Okay, understood? Now next, now 5.14, look at this, if the magnet turn through an angle 180 degree, that is, this is the north pole and this is the south pole. Okay, so here north pole pointing towards north, so neutral point is obtained is on the perpendicular bisector position. Okay, so look at this, here H equal to, look at this, here H equal to mu naught by 4 pi m by r cube. Now look at this, H equal to 0.36 Gauss, and this is the mu naught by, suppose this is the R1, mu naught by 4 pi, this is the m by R1 cube. Now 0.36 equals to mu naught by 4 pi, this is the 2m by r cube, so this is the mu naught by 4 pi, this is the m by r1 cube. Okay, now this cancel out. So look at this, 2 r1 cube is equal to r cube. So 2 to the power 1/3 into r1 equal to r. Now 2 to the power 1/3 r1 equal to 14. So look at this, r1 equal to 14 divided by 1.26 equal to almost 11 centimeter. Understood? Now next, look at this is a short bar magnet of magnetic moment 5.25 into 10 to the power minus 2 joule per Tesla. Now we have to calculate the distance of points on the axis and on the perpendicular bisector position where magnetic field makes an angle 45 degree. Now look at this, first of all on the axis, look at this, as angle made is 45 degree, so this magnetic field equal to horizontal component of earth magnetic field. Now look at this, the magnetic field on the axis, this is the mu naught by 4 pi, and this is the 2m divided by r2 cube is equal to He. Okay, where r2 is the distance of this point from its center. Okay, here H equal to 0.42 Gauss. So this is the 10 to the power minus 7. Now this is the 2 into m. What is the m? m equals to 5.25 into 10 to the power minus 2 divided by R2 cube is equal to 0.42 into 10 to the power minus 4. Okay, now R2 cube equal to, look at this is the 10.5 and look at this divided by 0.42 and this is the 9.4, so this is the 10 to the power minus 5, so this is the 10 so this is the 105 divided by 0.42 into 10 to the power minus 6. Now R equals to, look at this, R2 equal to third root of, this is the third root of 105 divided by 0.42 into 10 to the power minus 6. Okay, and this is the 5 into 10 to the power minus 2 meter, so this is the 5 centimeter. Okay, next, now look at this, at this point magnetic field due to magnet is equal to horizontal component of earth magnetic field. Now look at this, here H equal to, look at this, H equal to mu naught by 4 pi, this is the m by r1 cube. Okay, now this H equal to this, so look at this is the mu naught by 4 pi and this is the 2m by r2 cube equals to mu naught by 4 pi and this is the m by r1 cube. Okay, now look at this is the 2r1 cube equals to r2 cube, so look at this, r1 equals to r2 divided by 1.26, sorry, this is not 5, this is the 6.3, so this is the 6.3 centimeter, therefore look at this, this is the, look at this, this is the 6.3 divided by 1.26, so this is the 5 centimeter. Okay, understood? Next, now 5.18, the earth magnetic field is 0.33 Gauss, angle of inclination is 0, so horizontal component is equal to 0.33 Gauss. This is a cable which makes an angle 10 degree with this line, carries a current 2.5 ampere. Now find the distance from this point where magnetic field due to this current is equal to horizontal component of earth magnetic field. Look at this, as current flow this direction, so field directed along this direction, so here B along this direction, the magnetic field due to earth along this direction, so look at this is the mu naught by 4 pi, this is the 2I by R is equal to, look at this, HE. Now this is the 10 to the power minus 7, this is the 2 into 2.5 by R, this equal to 33 into 10 to the power minus 4. Okay, now R equal to, look at this, 5 divided by 0.33 into 10 to the power minus 3. Okay, so this is the 15 into 10 to the power minus 3. So this is the 1.5 into 10 to the power minus 2 meter, that is 1.5 centimeter. Okay, now magnetization capital M. When a magnetic substance is placed in a magnetic field, the magnetic moment induced in the magnetic substance per unit of its volume is called magnetization or intensity of magnetization. So look at this, M equal to magnetic moment per unit volume. If the substance has area of cross section alpha and length L, so its volume is L into alpha, and magnetic moment, look at this is the pole strength Qm into L. So look at this is the Qm by alpha. So magnetization is the pole strength induced by per unit area of cross section. Now unit of pole strength is ampere meter, unit of area of cross section, this is the m square, so unit of magnetization is ampere per meter. Okay, and its dimension A L minus 1. Okay, now magnetic intensity. If B be the magnetic field at a place, then magnetic intensity H equal to B by then magnetic intensity H equal to B by mu. In a free space, if the magnetic field is B naught, then magnetic intensity H equal to B naught by mu naught. So H is independent of medium. Okay. Now susceptibility. The susceptibility Chi is equal to ratio between intensity of magnetization divided by magnetic intensity. So the susceptibility equal to capital M by capital H. So it has unit ampere per meter. It also has unit ampere per meter. So it is dimensionless quantity. The susceptibility of iron and steel is almost equal. But susceptibility of iron or steel greater than the susceptibility of nickel or cobalt. Okay. Now relative permeability. The relative permeability mu r is equal to permeability in the medium divided by permeability in the free space. So mu r equal to mu by mu naught. Okay. So it also has a dimensionless quantity. Now we have to express the relation between relative permeability and susceptibility. Okay. Suppose magnetic field in free space is B naught. Now the magnetic field inside the material B is equal to magnetic field in free space plus induced magnetism. So this is the mu naught into capital M. Now divide this equation by H. So this is the B by H equal to B naught by H plus mu naught M divided by H. Okay. Now look at this. This is the mu. This is the mu naught and this is the mu naught into mu naught into chi. Now divided this equation. Now mu r equal to mu by mu naught. So this is the 1 plus chi. Look at this. So mu r is equal to 1 plus chi. Understood? Now retentivity. When a magnetic substance is removed from the magnetic field, the residual magnetism in the magnetic substance is called retentivity. The retentivity of steel is greater than the retentivity of soft iron. That is why steel is used to make permanent magnet and soft iron is used to manufacture the electromagnet. Now coercivity. The opposite magnetic field applied to the magnetic substance to nullify its residual magnetism. Okay. So coercivity of steel is much more than the coercivity of soft iron. Look at this. If a magnetic intensity is applied in a magnetic substance, the magnetic field inside the substance increases with increase of the magnetic intensity and finally gains the saturation value at the point P. If saturation value after P. Now if the magnetic intensity decreases from this value, the magnetic field also decreases but at the slower rate. When H equal to 0, look at this, B equal to OQ represents retentivity of the substance. Now to nullify this residual magnetism, H is equal to OR, opposite magnetic field applied to the magnetic substance. So this represents the coercivity. Okay, so coercivity equal to OR equal to minus H. Now magnetic field again increased in the opposite direction. The magnetic field inside the magnet increases maximum value in opposite direction at the point S. Now if H decreases, it's again, look at this, H0, then B equals to OQ equal to OT, also represents retentivity of the magnetic substance in opposite direction. Now to nullify this retentivity, the opposite magnetic field is OU, represents coercivity. Now complete magnetization and demagnetization, BH graph forms a loop called hysteresis loop or BH loop. The area bounded by BH loop represents the energy dissipation per unit volume in the magnetic substance. The area of the BH loop for soft iron is very small in comparison to the area of BH loop of steel. That is why the core of the transformer is manufactured by the soft iron instead of steel. Okay. Now diamagnetic substance. The substances which repelled by magnet is called diamagnetic substance. The substances which weakly repelled by the magnetic field is called diamagnetic substance. Diamagnetic substances are bismuth, copper, lead, silicon, nitrogen, etc. When magnetic field applied in the magnetic substance, the electron which have orbital magnetic moment in the direction of magnetic field slows down, and opposite to the direction of magnetic field speed up. So magnetic moment developed opposite to the applied magnetic field. That is why magnetic substance repelled by the magnetic field. The most exotic diamagnetic materials are superconductors. When these substances are cooled at very low temperature, they exhibit superconductivity. So these substances have property of superconductivity and super diamagnetism. So mu equal to -1. So chi equal to -1. Therefore, the superconducting material repels by magnet as well as repelled by the magnet. Therefore, the perfect diamagnetism in superconductor is called Meissner effect after the name of its discoverer. Superconducting material can gainfully exploit variety of purposes such as for running magnetically levitated superfast train. Now paramagnetic substance. Paramagnetic substances are weakly attracted by the magnet. Aluminium, calcium, sodium exhibits the paramagnetism. The susceptibility of paramagnetic substance chi equal to C mu naught by T. Therefore, susceptibility proportionate 1 by T. Therefore, susceptibility of paramagnetic substance is inversely proportional to its absolute temperature. This is known as Curie law, and C is the Curie constant. Okay. Now, paramagnetic substance has own magnetic moment due to orbital motion of the electron, but no magnetization seen as random orientation of the magnetic moment. When a magnetic field is applied in a paramagnetic substance, then the magnetic moment orient along the direction of magnetic field. That is why paramagnetic substance is weakly attracted with the magnetic field. Okay. Now, ferromagnetic substance. The substances which are strongly attracted by the magnet called ferromagnetic substance. Iron, nickel, cobalt are the ferromagnetic substance. Ferromagnetic substances has magnetic domain, but there is no resultant magnetic field obtained due to a random orientation of the domain. When magnetic field is applied on the ferromagnetic material, magnetic domain orient along the direction of the field. So that is why they are strongly attracted by the magnet. Now Curie temperature, the temperature at which ferromagnetic material is converted into paramagnetic material is called Curie temperature. The susceptibility of ferromagnetic substance C T minus Tc, where Tc is the Curie temperature and T greater than Tc. The Curie temperature of iron is 1043 Kelvin and for cobalt it is 1394 Kelvin. Okay. Now comparison between ferromagnetic, paramagnetic and diamagnetic material. First of all, attraction. Look at this attraction. Here these substances are strongly attracted by magnet. These substances are weakly attracted by magnet and these substances are weakly repelled by magnet. Now look at this. Here B. Look at this, here B greater than B naught. Here B greater than B naught and here B less than B naught. Okay. Now mu R. This is greater than 1. This is greater than 1. This is less than 1. Okay. Now susceptibility. Now susceptibility chi. This is greater than 0, this is greater than 0, this is less than 0. Okay. Now retentivity. Retentivity present here. No retentivity, no retentivity. Coercivity of this substance exist, no exist, no exist. Okay. Look at this Ncert numerical 5.23. Look at this, number of atoms in the sample is 2 into 10 to the power 24. Now what is the maximum dipole moment? The maximum dipole moment is equal to this into this. Now it is placed in a magnetic field 0.64 Tesla at temperature 4.2 Kelvin. Now at saturation the magnetic moment is 15% of total magnetic moment. Now what is the magnetic moment if this sample is placed at this magnetic field at temperature this? Okay. Now first of all maximum magnetic moment M equal to, this is the N into M dash. So look at this, this is the 2 into 10 to the power 24 into 1.5 into 10 to the power minus 23 joule per Tesla. Okay. This is the 30 joule per Tesla. Now what is the M1? M1 is the 15% of this value. Okay. Now look at this, M1 is equal to 15 by 100 and this is the 30. So this is the 4.5 joule per Tesla. Now M1 known, T1 known, B1 known. Here B2 known, T2 known. We easily calculate the M2. In paramagnetic substance, magnetic moment is directly proportional to magnetic field and inversely proportional to temperature. So look at this, M2 by M1, this equal to B2 by B1 into T1 by T2 because T is inversely proportional to this. Now put the value. Look at this, this is the M2 and M1. What is the M1? M1 equal to 4.5, B2 is 0.98 and B1 is 0.64. What is T1? Look at this, 4.2. Now what is T2? This is the 2.8. Okay. Now look at this and this. This is the 2 and this is the 3. Okay. Now M2 equal to, look at this. This is the 4.5 and this is the 49 by 32 and this is the 3 by 2. Okay. this is the 10.3 joule per Tesla. Okay, understood? Now 5.24. The radius of rolling ring is 0.15 meter. Number of turns in the ferromagnetic core is 3500 and relative permeability of the core is 800. The magnetizing current is 1.2 ampere. We have to calculate the magnetic field in the core. Now in rolling ring, the magnetic field in the core B equal to, this is the mu1 mu naught Ni divided by 2 pi r. Now put the value. This is the 800, this is the 4 pi into 10 to the power minus 7, and this is the 3500, and current is, look at this, 1.2 divided by 2 pi capital R. Now 2 pi, this is the 2. Okay? Now look at this. This is the 1600 into 10 to the power minus 7 into 3500 into 1.2 divided by 0.15. Okay? Now look at this, 10 to the power minus 7. This becomes 0.16 into 3.5 into 1.2 divided by 0.15. Okay? So this is the 4.48 Tesla. Okay? Now electromagnet. If a soft iron core is wound by an insulated wire and current passes through this, then the soft iron core behaves as a magnet. The end where current passing through anti-clockwise represents N pole and the other end is the south pole. Its strength increased by increasing the strength of current or number of turns passing through it, or use the material of higher permeability. Okay? Now its advantage, the polarity of the magnet change by changing the current. Now what is the difference between electromagnet and permanent magnet? The strength of permanent magnet is fixed, but strength of electromagnet may be changes by changing the strength of current. The polarity of the permanent magnet is fixed, but the polarity of the electromagnet may changes by changing the direction of current. The shape of the permanent magnet is fixed, but shape of the electromagnet changing according to the need. Okay? Many thanks for watching this video. I hope this video will be beneficial for you, because all types of numerical in this chapter with theory was discussed elaborately. This discussion helps you in CBSE, in NEET, in main and in advanced. Please like, comment and share the video. And if you are new, don't forget to subscribe my channel.